Last problem in the test 2 review of the Physics Bootcamp. The question says a force of 10 newtons at an angle of 65 degrees above the horizontal is applied to a block of mass 3 kilograms. So let's write that down. The block is 3 kilograms. The force is applied at an angle, 10 newtons at an angle of 65 degrees. And it's lying on the surface, and the friction mu k is equal to 0.2. What is the work done by the force F? What is the work done by friction? Okay, and what is the final velocity of the block after being dragged for 20 meters? Okay, so the first thing we can do is we can find the work done by the force F. The work done by the force F is F d cosine theta, right? The force times the distance that you drag it times cosine of the angle between the force and the distance, right? So you're dragging it horizontally for the distance of 20 meters. So only the x component of the force is actually doing work. 10 cos 65, you see? 10 cos 65. So you have work by the force is equal to 10 times 20 times cosine of 65 degrees. So only the component of your force along the displacement actually does work. 10 times 20 times cosine 65. 84.524 joules. That's how much work you do. Now, how much work does friction do? This is the tricky part of this problem, right? This first part is not tricky. A lot of people would go like this. The work of friction, they would say, well, friction is back this way, mu k n, okay, coefficient of friction times the normal force. So then they would say, okay, friction is this way, the distance is this way, 20, so they would go negative mu k n d, right? So since the friction is opposite to the force, to the distance, the friction does negative work, and the angle between them is 180, right? Friction is always opposed to the motion. What's cosine of 180? Okay, it's -1, right? So that's where this negative comes. So far, they are doing good. A lot of students would set it up that way, minus mu k n d. The next step, they would put this, minus 0.2. What are they going to put for the normal force? Well, they're going to put the normal force, the weight of the block is 3 times 9.8. So the weight of the block, 29.4 newtons. Okay? Here's the step that a lot of people would put wrong. The normal force, you're going to put equal to 29.4. So the normal force, they're going to put equal to your weight. 29.4. The distance, they're going to put 20. Okay? If you did this, your answer would be wrong. Okay? Why is that? Well, here is the answer. Because you're exerting this force at an angle, part of your force is going into lifting the block, right? That's very, very important. This horizontal component of your force actually drags the block. The vertical component of your force, which is equal to what? This vertical component is 10 sine of 65. The vertical, right? What does that do? Well, that one aids the normal force. Two of them together hold up your weight, right? So the sum of the two vertical forces must equal to your weight. N plus 10 sine 65 equal 29.4. What is that going to do to the normal force on the block? It's going to reduce it, right? When you put here 10 sine 65, it goes over there. It helps to reduce it. So whenever you exert the force on something at an angle, right, you tend to give it a bit of a lift, right? If you exert enough force, you tend to lift the object from the surface, right? So since you're giving it a little bit of a lift, the normal force reduces. If the normal force reduces, the work done by friction is also going to reduce, right? It's going to do less work. So let's calculate what the normal force is. It's equal to 29.4 minus 10 sine 65. Okay? So 29.4 minus 10 sine of 65, 20.337 newtons. So instead of the normal force being equal to 29.4, it's now only 20 newtons. Then we put the 20 in here, okay? So 20.337, that's for the end. The distance is still 20. Multiply them. And the work of friction is negative 81.348 joules. Where does that energy go? Where does that work go that friction does? Well, it shows up as heat in the system, right? When you drag an object, it makes heat, the object heats up. When you touch the object, it is hotter. When you touch the surface is also hotter, right? So the problem could also ask the question this way. How much heat is lost to friction? How much energy shows up as heat in the system? All of those are different ways of asking this question, what's the work done by friction? Okay, so you would say 81.348 joules of energy shows up as heat in the system. Okay, so then what's the next question? What is the final velocity of the block? Well, basically we're pretty much set. What you do is you say the total work done on the block, work total, is equal to change in kinetic energy of the block. So 84.524 is the amount of work you do, okay? And the amount of work that friction does is negative 81.348. That's equal to half times the mass times the final velocity squared minus half times the mass times the initial velocity squared. What was the initial velocity? The initial velocity was 0, right? Right now, I am ignoring the fact that we had to originally beat the static coefficient of friction. So ignore that for a second. Let's say we made it move, and then we're concerned after that what happens. So the initial velocity is more or less approximately 0, and then basically went like this. Okay, we moved it, and then don't worry about what is happening to the static coefficient of friction for now. So the initial velocity is 0. What is the mass of the object? 3 kilograms, right? So you put here 3. Well, you just basically subtract this then. 84.524 minus 81.348. You get 3.176 is equal to, this one is 1.5 V final squared. So divide that by 1.5. Square root it, and the final velocity is 1.46 meters per second. Okay, so the final velocity is 1.46 meters per second, and then this is how you do this problem. So the trickiest part here is to make sure that you're always analyzing what is happening to the normal force on the block. Okay, thank you.